What's up YouTube, it's ASX Portfolio. So today is part 4 for the implementation of the efficient frontier in Python, and today we're going to be focusing on actually just printing our results from the maximum Sharpe ratio portfolio and the minimum variance portfolio. So just going over, remember that the maximum Sharpe ratio portfolio, that was where we were focusing on the trade-off between returns and volatility. We want the highest amount of returns for a given level of volatility. And for the minimum variance portfolio, we want to know, given the asset selections that we have, what is the absolute minimum variance, minimum volatility that we can have holding a portfolio, and what are the weights of those assets. So now that we've got those two things, let's define what a function is that we can actually start outputting these results. So we're going to come down here. Let's define a new function, and let's say, let's call this calculated results. And what we want to import, obviously, is the mean returns. We want the covariance matrix, we've been using that a lot. We want to import the risk-free rate. We're just going to make that equal to 0. And obviously we want the constraint set. And we've made that 0 between 0 and 1. So what do we want to do in this function? Let's define exactly what we want to do. So we want to read in all the information, read in mean, covariance, matrix, and other financial information. And what do we want to output? We want to output the max Sharpe ratio, the min volatility portfolio, and later the efficient frontier. Efficient frontier. Excellent. So let's start working on the maximum Sharpe ratio output. So all we need to do is come up here, and we've already defined what the mean returns and covariances are. We can actually get rid of the weights and returns there, and let's bring this down into here. So instead of calling it result, let's call it something more meaningful. Let's say max Sharpe ratio portfolio. And to separate there, I'm going to use an underscore. Well, I've been using camel case, I've been doing very well until now. So the max Sharpe ratio portfolio, and all we need are those two parameters there. So let's actually get out useful information from that. So if you remember, the maximum Sharpe ratio portfolio is actually outputting the results of that minimization function. So there's a couple of things that we can draw out from there, if you remember. So the X actually contains all of our weights. So if we just do that, max Sharpe ratio, and we grab the weights, what we actually want is we want to know not what the allocation is straight away, but more importantly, what the portfolio returns and volatility were. So if we grab the portfolio performance function, and if you can see there, instead of putting the weights, we're just going to directly substitute the weights that are coming out of the max portfolio optimization. And we can call this, what did we have first? We had returns and then standard deviation. So let's go max Sharpe ratio returns and max Sharpe ratio standard deviation. Awesome. So now we're going to focus on what the allocations are for all the weights that came out of that portfolio. So let's use that information and let's create a pandas data frame. So we're going to call it max Sharpe ratio allocation. Okay, and what we're going to do is we're going to create a pandas data frame. So data frame. And what we want is we want to actually have those weights with the associated names. So let's take that information again for the weights. And for the index, we want to be taking the same index that is in the mean returns data frame. So the index is going to be mean returns dot index. Excellent. And the last piece of information is we need to name the column. So columns equal, let's call this piece of information allocation or weightings. Doesn't matter. Allocation. Okay, so now we've got a pandas data frame. Let's just return that and make sure that it is doing what we're saying. So let's return the returns, the standard deviation, and the allocation. Okay. So we'll just wipe that out for a second, and we're gonna print that function. So hopefully we get our returns standard deviation, PD not defined. Oh, we better import pandas data frame. So I didn't realize there, sorry, we were using pandas data frame from the pandas data reader. So import pandas as PD, save that down. And it may ask us here that we need to add it into our list of dependencies. No, it's all good. So here the tuple's been released. We've got a portfolio for the maximum Sharpe ratio, 7% return, 38% volatility, and then the weightings for CBA is pretty much 0, BHP 1, and 0. Now that's a little bit annoying, having this scientific notation that tells us it's almost 0 times 10 to the power of negative 17. So let's, that's 0 for all intensive purposes. So let's get rid of that kind of noise. So what we're going to do, we're going to access the pandas data frame, and we're going to clean up that data. So here's the pandas data frame. Let's go into that column, and we've called it allocation. So dot allocation we're going to change. Let's now say make a list, and we're going to round. We're going to round I for I in max allocation dot allocation. So for all of these numbers, what we want to do is round them to a certain number of decimal places, and I reckon it's probably worth going 2 for now. And in fact, what we should do is let's change them to percentages straight away. So we'll times I by 100%, and we'll actually round to 0 there. So let's try that now. As soon as we've got this working, what we're going to do is actually focus. There we go. That's a lot cleaner. So symbols 0%, 100%, 0. So what we're going to do is we're actually going to implement this now for the minimum volatility portfolio, and we can pretty much just carbon copy all of this. So let's just make some comments here. So this is for the max Sharpe ratio portfolio, and now we want to get information for the min volatility portfolio. So let's call the portfolio min vol portfolio, and remember, min variance portfolio as we called it up there. Let's target that function. Minimize variance is what we call the function. Min vol, let's copy that terminology. Min vol returns and max vol returns is calculated from min vol portfolio weightings. That'll be calculated in that function. same mean return, same covariance matrix. That means our min-vol allocation is going to be min-vol portfolio X, the mean returns index again, and min-vol allocations is going to be rounded like that. Excellent. So now let's return all that information as well. So you can see here we're getting a few data points, but that's all right. Let's print that out and see what we get. Excellent. So we've got a negative return here for the minimum variance portfolio, but a reduced volatility, you can see, so 27%. And the allocations are here, very neat. While we've got this, maybe it's worth actually cleaning these up too, or we can actually do that later. No, we'll do that now. So let's round those functions as well, because they're kind of annoying to see. So we're just going to round. Let's turn them into percentages, 2 decimal places. So round times by 100, 2 decimal places. And we're going to do the same thing for the min volatility returns. And I'm just copying the respective min-vol standard deviations there. Let's return that, and hopefully it looks a lot neater for us, and it's in percentages now. Oh, much easier to see. So 7%, 38%, and the allocations, minus 6%, 27%, 28%, and the allocations. Great, easy to see. So this function is calculating all our results. We can now get rid of all of this stuff above. Now this function is just going to make it easier when we come to graphing all our results in later tutorials, access to that data. So now that we've actually passed that calculated results, let's move on to the most important thing, which has been the efficient frontier. So we're going to have to actually start up a new optimization problem for this. So it's kind of like the combination of both of the things we've been talking about. So I've got the formulation up here in the right-hand corner of the screen, and I'm going to keep it up there while we implement it. So this is the one that I introduced in the modern portfolio theory video, and this is the one that we're going to implement. So just again, for each target return, what we want to do is actually minimize the variance of the portfolio. So we're going to go through a whole bunch of target returns, calculate those, and at each time step we're going to calculate the parameters that minimize the portfolio variance. What we're going to get from that, we're going to get a return for our portfolio, and we're going to get a volatility for our portfolio, and we're going to plot those two on an axis, and then we're going to see how that actually creates the efficient frontier. So let's jump straight into the optimization. So we're going to go above that calculated results now, and we're going to say define a new optimization problem, and we're going to call it efficient frontier, or yes, efficient results, maybe efficient optimization, let's call it optim. Okay. Let's, again, as we've been doing, we're going to have the mean returns and covariance matrix. We're going to have a constraint set that's defined. And one more thing now that we're going to add is actually a target. So this target is going to be our return target. So let's actually be more specific. Return target for our portfolio. So let's just have a little bit of a think what we want to do here. Let's define our function, always good habit. So for each return target, we want to optimize the portfolio for min variance. Okay. Excellent. So given our target, we want to be above that. So that's where the constraint in the top-hand side you can see on the screen. And we want to, of course, make sure the other constraints that all the sums of the portfolio weights are equal to 1. And we want to minimize volatility. So let's implement, as we've been doing, we want the number of assets. So we're going to need the length from the mean returns data frame. We want the args as per usual, which is the mean returns, covariance, matrix, and the constraint set. Oh, constraint set, sorry, comes later. What we will need is to define what the portfolio target range is. So, because we don't know, we need a function that actually returns what the portfolio returns is given its weights as a parameter to optimize for. So before we do that, I'll just show you what the constraints are going to look like and to explain why we need that function. So constraints, can't spell. So remember, it's a dictionary type, and the first one, as you can see in the top right hand corner, is a strict equality fun, and we want a lambda function that takes in variable x, which again has always been the weights of our portfolio allocation, and we want to have a portfolio return function that just takes in those weights. So because we want that to equal our target function or make it less than or greater than or equal to, with this function right here, I'm just making it the strict equality on the bounds, but we could just as easily make it greater than or equal to. But for now, let's just keep it simple, and we're going to minus the return target. So this is just saying we must have our return target equal to the portfolio return weightings. So the other one, of course, is going to be what we've been doing all along, and I'm just going to take it from up here, type equality. And that's just going to be that all our weightings are equal to 1. Seen that before. So, cool. We need a portfolio return function. It's very similar to how we had portfolio variance defined here, and we needed to actually define what the weights are. So in a similar fashion, we're going to copy this function. Instead of calling it portfolio variance, we're going to call it portfolio returns. And instead of indexing to the first of our portfolio performance, which is standard deviation, we're just going to grab returns. So very, very easy there. Excellent. And I am noticing that we're actually, because these variables are going to be defined within arguments for the function, for the constraints, we're actually going to have to put this function within this function. Now, the reason I'm doing that, guys, is because in this function, mean returns and covariance matrix are going to be defined parameters. So we don't need to actually import that into the function as a parameter. The reason I'm doing that is because we only want a function down here that's dependent on that variable. Very, very interesting. Actually, I'm gonna test something. We're gonna keep it out here. I'll just try something. We're going to put the mean returns and covariance down into this function. That should be fine. Okay, so constraints, as per usual, we want the bounds, which is going to be the constraint set. We want, remember the bounds are going to be a set of tuples for all assets. For asset in range number of assets. And we're going to want the result of each optimization. So fopt result equals psi.minimize, and the function we want to minimize over is portfolio variance. So as above, portfolio variance. And remember, that's the parameter that it's going to change the weights of. We want to give an initial guess for all the weights, and remember that's just going to be num assets, a list of 1 divided by all of the num assets. So an even portfolio allocation is a first pass guess. We want the args to equal args going into that function. What else do we want? We want the constraints equal to the constraints, and we want the bounds to equal to the bounds. So method is going to be sequential least squares. We need constraints and bounds. Bounds equal bounds, and constraints equal constraints. And just making sure I've spelt that there all correctly. Great. Return f optim. Okay, let's test that function just to make sure that it's working. So just comment that out. Print f optimization, efficient optimization, mean returns, covariance, and that should be it. So it's going to print out that nasty optimization stuff, but remember we're only interested in one missing required. Of course, we've gotten the target portfolio. So let's say target is 10%. I don't know over that data range where it can even reach 10%. No, it can't. So it can only reach 7%. Let's grab 0.6%. So generator has no length. Constraint set. Oh, silly. I should define bound equals constraint set. Sorry for that. So we're trying to optimize a portfolio to 6% returns, and we're minimizing the variance. Again, no luck. Bounds for asset in range number of assets. What is going on? Oh, I need to make it a tuple. There we go. So we're putting in a list into those bounds. Sorry about that. Yeah, have forgotten. Takes 1 positional argument, but 3 were given. Of course, so mistake upon mistake. Don't forget to add in mean returns and covariance into your portfolio return outside of the function. Excellent. Okay, we've got it working. So here we've got a portfolio of allocations to get us to that target return. Okay, excellent. So what we're going to do is we want to place this information in this calculation function, but we actually want to iterate between all the returns from the minimum variance portfolio return, which should be, you know, the lowest return that we're interested in, all the way up to the max ratio return. So the way we're going to do that is we're going to have to create another function that actually returns all of the portfolios on the efficient frontier that we're interested in. And the way we're going to do that, we're going to define a target return list by making a numpy array of lin spaces between the minimum return volatility and the maximum return volatility. And the amount of steps that we want to take through that depends how clean we want our curve, but let's just say 20 for now. So we now want to define, we could do it in this loop here. So the efficient optimization, we want to take the mean returns and covariance. So for target in target returns, we want to build up this efficient frontier, this optimization. So what we want to do is we want to store all this information. So let's create a list called efficient frontier. Let's call it efficient list. Very creative. So for each target function, we want to append this information. Append those results, and that should be good. The key bits of information that we're looking for is we've already defined what the return is going into that function. We just need to specify what the volatility that we've calculated is. So we're only going to access fun, which, remember, that returns the objective function value for that minimization problem. So in this case, because we're actually optimizing over the portfolio variance, we're going to return the portfolio variance. So let's make sure that that actually works. Let's run this function, get rid of that. And we should see a list of values for volatility here. So now we're actually having to undergo 2 optimizations here, plus another 20 for this return. And that seems to have worked out perfectly well. So we can see that for all these different targets, returns that it's tried between, what values has it tried? Between negative 2.25% return and 7% return, it's stepped out all of these volatilities from its optimization. So all we need to do now is plot all this information on a graph, and we're going to save that for the next tutorial. So thank you very much for listening to ASX Portfolio. Let's get back into this in part number 5.